Hi everyone, today we have a lot to talk about. This concerns the masses of stars, how we determine stellar masses, and how our sun compares with other stars, what the biggest stars are, and what the smallest stars are. And in determining the masses of stars, we look at binary systems. And we can also figure out masses of stars using other means, but binary systems provide the most accurate way of determining stellar masses. If you can find something orbiting around a star, then you can figure out the mass of the star using Newton's law of universal gravitation and combining it with the centripetal force equation, and that allows you to figure out the mass of the object being orbited, just as we figure out the masses of planets in our solar system by finding moons around those planets and watching the moons orbit around. So there are a number of different types of binary systems. There are visual binaries where you can actually see two different stars in the telescope. An example of a visual binary system would be a couple of basically the stars in Mizar. The stars in Mizar are a visual binary. If you look at them in a telescope, you'll resolve the star Mizar into two separate stars. In fact, we're going to have more to say on Mizar soon. There are also spectroscopic binaries. Those are situations where the stars are too close together even for a good telescope to be able to resolve them into separate stars. Because remember, the distance between us and stars is so vast that you generally can't resolve a star itself. Instead, when you see a star being kind of wide like a disk in a telescope, that's an optical effect of the overexposure of the image itself. Now, there are also so-called optical binaries. These are not real binaries. These are situations where you just happen to have two stars along the same line of sight. A nice example of this is the system Mizar and Alcor. We've discussed Mizar and Alcor before. It's been on your constellation quizzes. And these are two stars that happen to be along the same line of sight in Ursa Major, in the Big Dipper part of Ursa Major, but they're not actually orbiting each other. It just so happens one of them is closer than the other. In fact, one of those stars is slightly closer than the other, and as far as we can tell, they are not actually gravitationally bound. However, if you look at Mizar itself, it does turn out that Mizar has a multiple star system in it, and we're going to discuss that soon. So here's another binary star, Kruger 60. So you can see actually over time how one of the stars moves around the other. This would be a visual binary. In other words, you can actually see that it's two separate stars in a telescope. In fact, here you can tell kind of an orbit of a system of stars. Now, how do we determine that a star is a binary star if you can't actually see two separate stars in a telescope? That's where the spectroscopic binary lies. When you have the two stars happen to be along the same line of sight, then neither one of them is moving toward us, nor is the other, nor are they moving away from us. They're kind of at the point in their orbit where they're moving side to side. Well, when that happens, you're not going to have any Doppler shifting of the spectral lines. That's going to be the situation in the bottom part of this picture. Notice that in this case, the spectral lines are together. They're merged together. But in the top part, this is a situation where you're dealing with a time later in the orbit or earlier in the orbit where one of the stars was moving away from us, giving a longer spectral line, whereas the other star is moving toward us, giving a shorter spectral line. When I'm talking about longer versus shorter, I'm talking about longer wavelength and shorter wavelength, because what we're measuring here are wavelengths of the various spectral lines. And as the stars orbit around each other, what happens is these lines go back and forth, merging together, coming apart, merging together, coming apart, etc. in a nice pattern. So here is Ursa Major again, and there's this is Mizar and Alcor, though they don't have it separated in this particular picture. But Mizar, again, you're dealing with a complicated system. If you have reasonably good eyesight, you can tell that there's another star there, Alcor. Again, that's an optical double. But in a telescope, Mizar is seen to have a close companion. That's a visual binary. We call those two components Mizar A and Mizar B. However, it turns out that with a spectroscope you can find that Mizar A and Mizar B are each spectroscopic binaries. So Mizar itself is actually a quadruple star system, and that's not even counting Alcor, which again with current knowledge we don't think is gravitationally bound to Mizar, but as better measurements are made we might end up having to revise that idea. So we've discussed Kepler's laws before. I'm going to skip through these slides for the most part and leave only a little bit of time in case you need to pause the video and read through some of this again and how we determine the Newton's version of Kepler's third law. You'd need to go back and combine Newton's law of universal gravitation with the centripetal force equation or acentripetal force equation. And we've also discussed center of mass before as well, where you have two people balancing on opposite sides of a seesaw, but the one who's more massive needs to be closer to the center in order for the other one to have any fun. Now, where that pivot is, in order for them to balance, that is the location of the center of mass. Same thing works for stars. In this case, you're not talking about the weight, but actually the force of gravity between them, which I guess you could say is kind of a weight, so to speak, in the middle of space. But it's, if you were to multiply the mass of one by its position and multiply the mass of the other times its position and divide by the total mass, the result would be a position which is equal to the center of mass. How you can determine that physically? Well, just find two different points in an orbit. The center of mass is always going to be on a line connecting the objects. Well, clearly, at some point, one of the stars is going to be over here while the other star is over here. Otherwise, things wouldn't balance at all. So the center of mass is going to certainly be along this line. And another point, if you were to cross a line going right here with a line connecting the stars right here, that can allow you to find the center of mass, because the center of mass in a binary system is not going to oscillate back and forth. In fact, if you put yourself in the reference frame of the center of mass will not move, and you'll just see the stars orbiting around the center of mass. You can do this in various simulations like the PhET simulation, the PhET My Solar System simulation, where we have two different stars orbiting around each other. I used Microsoft Paint to superimpose these pictures, and I drew lines connecting the centers of the stars, and then did that at two different points, superimposed the pictures. Where they cross must be the center of mass. So that's how you can find the center of mass, and astronomers can do that certainly with visual binaries. Now, the star Sirius, the brightest star in the night sky, is actually a member of a binary system. It has a very, very faint companion. It wasn't even discovered until the 19th century. But that very faint companion, which happens to be a special type of star called a white dwarf, we'll have a lot more to say about those in a future discussion, but it's very faint, but relatively massive compared with how bright it is. And the center of mass is outside the surface of both of those stars, and they orbit around each other over a period of time. Now, I should mention that Kepler's third law actually only gives you the total mass of the system, not each individual mass. Instead, you need to watch over time as they orbit around each other to figure out more information. For example, where the center of mass is, that can help you to determine the individual masses if you combine that with the knowledge gained of the total mass from Kepler's third law. So again, here's the Doppler shift from a system of stars. Now, some binary stars actually interact with each other. For example, there's a star V Hydri who has its outer layers interacting with an orbiting companion, and occasionally that results in fireballs that are so hot that they're mainly emitting UV light being launched out into space. This is an artist's impression of that system. So, pretty cool. So just a quick summary of what we've discussed so far. Astronomers can determine masses of stars in a binary system by taking a look at the orbit. Kepler's third law will tell you the sum of the masses, and based on how the center of mass works, where the center of mass is, the ratio of the positions of each star from the center of mass is inversely proportional to the ratio, or actually the ratio of their positions from the center of mass is equal to the inverse of the ratio of the individual masses. So combining that with what we get from Kepler's third law can allow us to determine the individual masses of the objects in the system. Now, a little caveat on that, that only works if you're dealing either that only works if you know the angle of inclination of the orbit. The Gaia spacecraft, though, is allowing us to determine a lot of that very precisely now, so that's no longer all that much of an issue. So here's a summary of what we were just talking about written down. If you need to internalize that, then please pause the video. Otherwise, we need to move on to discuss stellar populations. Now, there are two main populations of stars. As you know, astronomers are extremely creative with their names, things like Very Large Telescope and Extremely Large Telescope, while they are similarly creative with their names for stellar populations. There are population 1 stars, and the other main type of star is population 2 stars. So these names were actually devised by the astronomer Walter Baade back in, I think, around the 1950s. But long story short, these populations are divided based on the amount of metals in a star's composition. So what's a metal? Well, remember what a metal is? A metal in astronomy is anything heavier than helium. So yeah, you can go around telling your chemistry teacher that oxygen is a metal in astronomy, and I'm sure that she or he will become very impressed and downgrade your average for the year. But in any case, population 1 stars are the metal-rich stars, the ones that formed reasonably recently, whereas population 2 stars are the metal-poor stars. Our Sun is an example of a population 1 star. So, roughly speaking, population 1 stars have about 2% of their composition in the form of metals. And again, roughly speaking, population 2 stars have about 0.1% of their composition as metals. And again, there's a lot of stuff in between here. So if it's roughly an order of magnitude from 2%, then we call it a population 1 star. If it's roughly an order of magnitude, yeah, I know there's some overlap here, from population 2, we call it a population 2 stars. And if it's really too close to being in between, then we call it an intermediate population. But we can really divide the great majority of the stars that are out there fairly cleanly into either population 1 stars or population 2 stars. Now, population 1 stars are the ones that formed relatively recently, and population 2 stars are the ones that formed a long time ago. How do we know that? Or why is that the case? Well, consider it this way. Remember, in the Big Bang, we basically formed only hydrogen and helium, and we formed small amounts of lithium or beryllium. All the beryllium was beryllium-7 that decayed, and a lot of the lithium has gotten consumed in nuclear interactions with other stars, though that's complicated because lithium is also produced in nova explosions. But in any case, the more metals a star has, the more recently that star formed. Because if a star formed, say, 12 billion years ago, well, there hadn't been all that many generations of stars out there to explode as supernova and pollute the universe with heavy elements, or cast off their outer layers and spread all kinds of dust that contains heavy elements into the universe. That hadn't happened all that much yet. But if a star formed, say, 3 billion years ago, well, there have been many generations of stars that have done this, cast out lots of heavy elements in the form of either supernova explosions or dust in as they cast off their outer layers, and you get a lot more metals out there in the star formation nebula as the stars form. Now, I know some of the more astute students might be wondering, well, wait a second, why should there really be a difference? Even though population 2 stars have formed, say, 12 billion years ago or whatever, shouldn't a lot of metals have been deposited onto their surfaces from these supernova explosions and their interactions with the various dust in the interstellar medium and stuff like that? Well, here's why population 2 stars, the old stars, don't have dust that has accumulated and given them lots of heavy metals. Remember, think about our sun. What is always coming out of our sun? The solar wind. The stellar winds end up blasting out with enough energy. Even when they're relatively quiet, the stellar winds are blowing out against any sort of metals and dust that would potentially be coming onto these stars. So once a star forms, the amount of metals is essentially locked into that star. And based on the amount of metals it has, you can get an idea of that star's age most of the time. Now, there's also a third group of stars that aren't really in the universe today. They are population 3 stars. These are the first stars that actually formed after the Big Bang. They would have formed sometime between, starting probably around 100 million years after the Big Bang, maybe a little bit less than that, and the first maybe a couple 100 million years or so after the Big Bang would have been the era of population 3 stars. The vast majority of population 3 stars, though, have exploded. Most of these exploded either as pair-instability supernovae and polluted the universe with lots of heavy elements, or the most massive ones, the ones that started off with masses of more than about 250 times the mass of our Sun, they ended up having photodisintegration in their cores, and that caused the cores to collapse and form relatively large black holes, and now we think that that probably did not actually result in all that much of a supernova explosion. But yeah, stars starting off with between about 130 and 250 times the mass of our Sun, which were a whole lot of the stars that formed in the very first stages of our universe after stars started forming, ended up going into pair-instability supernovae. These ended up blasting lots and lots of heavy elements out into the interstellar medium, intergalactic medium, and we ended up then getting the next generation of stars, which is the population 2 stars. Now, try to keep in mind that there is a point of confusion here. The most recent stars are the population 1 stars. The older stars are the population 2 stars. And then the hypothetical population 3 stars, which are basically no longer with us, those were the very first stars to form. So yeah, it's kind of a backward type of system, similar to the stellar magnitude system in a way. But I guess astronomers can sometimes be crazy on that sort of thing. So, quick quiz. Is our Sun a population 1 star, population 2 star, or population 3 star? So, take a couple seconds to pause the video if you need to think about that. And I will tell you now, our Sun is a population 1 star. In fact, the stars that form in the spiral arms or near the spiral arms of galaxies are generally population 1 stars. However, most of the stars around our galaxy's central region, as well as the stars in our galaxy's halo, this kind of very thin spherical halo of stars that surrounds the core and also farther out regions of our galaxy, those are generally population 2 stars. What about stellar masses? How massive can stars get? There are stars that are much more massive than our Sun, but those are quite rare. In fact, our Sun is more massive than the great majority of stars in our galaxy. In fact, there are a handful of stars in our galaxy with masses of more than 100 times the mass of our Sun, but again, only a handful. In fact, there are no stars within 10 parsecs of us, that is about 33 light years, that are more massive than 4 times the mass of our Sun. So that's something to keep in mind. However, I will tell you that a whole lot of the stars that you see in the evening sky are more massive than that. In fact, all of the stars that you see in a light-polluted area such as Northern Virginia are more than 4, at least the ones that are in Orion, is what I meant to say. All the ones that you see in Orion from Northern Virginia are more massive than 4 solar masses. So that's something to keep in mind. And what we see in the night sky is not a good representation of what's out there. So we've seen this list before. Now, here is a pie chart showing the stellar mass distribution. In fact, this is an old pie chart. But even in this old pie chart, you see that the great majority of stars are less massive than our Sun. We have 41 plus 19 gives you 60, plus another 28 gives you 88. So even in this situation, 88% of stars out there are less massive than our Sun. In fact, more recent studies are showing us that there are even more in the way of less massive stars than we thought. We're now realizing that stars less than about 0.3 times the mass of our Sun, that is 0.3 solar masses, make up about 80% of the mass of stars that are out there. So That's the case in giant elliptical galaxies, at least, and giant elliptical galaxies have lots and lots of stars. Even our Milky Way galaxy is very much tilted toward the less massive stars. Now, the smallest stars, at least the least massive stars, are stars that are about 1/12 of our sun's mass, so about 0.08 solar masses. And these are the smallest, or the least massive that a star can be in order to have enough gravity to convert potential energy into kinetic energy and get the temperature in the core high enough that you'll be able to start the proton-proton chain. We'll talk about stars in a little bit that have masses less than this, but are still more than about 12 or 13 times Jupiter's mass. They're a special class of objects, and they're not really stars, but nonetheless we'll speak of them. They're quite interesting. What about stellar sizes? How large and how small can stars get? And where does our sun compare in the midst of these? So even in the largest telescopes, the vast majority of stars out there still appear just as tiny points of light. In fact, in the Hubble Space Telescope, which isn't going to have the atmospheric blurring, the diameter of a star is simply going to be given by the diffraction limited diameter, depending at whatever wavelength is being observed for that star. But there are a few cases where we can determine a star's diameter directly by imaging. The biggest stars out there, in other words. Betelgeuse, a well-known star. You've certainly had it on the constellation quiz. Nice big bright star in Orion. You've heard a lot about it lately in the news because of various changes in its brightness. But this is a very large star. If you were to place it in place of our sun in the solar system, its outer layers would go past the orbit of Mars. It's an example of a red supergiant star. Betelgeuse will eventually go supernova. And red supergiant stars, in fact, are the largest stars in the universe. They, at the biggest extents of them, the biggest ones can be as large as Saturn's orbit around the sun, or even larger than that. Now, here is a picture of Betelgeuse taken from the Hubble Space Telescope about 2 decades ago. And you can see there's a little bit of structure there. There's a more recent image that was taken in late 2019 as Betelgeuse started to undergo some weird changes in its brightness, and we're seeing that it's not exactly a spherical shape at this point. It has this kind of polar outflow, so to speak, and it's brighter in one spot and dimmer in other spots. So it's quite an interesting object. Here's an artist's conception of what Betelgeuse might have looked like before it started undergoing these weird oscillations and changes in brightness. If you were to look at Betelgeuse from, say, Neptune's distance from the sun, so that's that type of distance, if you were to look at Betelgeuse from 30 astronomical units away. In other words, it's a really, really, really big object. So the star Mira in Cetus also has a little bit of structure to it, and we can also discern some structure in other stars using radio interferometry. We'll talk about that soon. And also we recently got a very nice image of the star Antares in constellation Scorpius. Antares is another example of a red supergiant star, which again, these are the largest stars in the universe. Not the most massive, but the largest. And an artist's conception of Antares as well. So very nice there. What about getting things down a little bit to size? In other words, we mentioned optical interferometry. There's a little bit of use with this in figuring out the diameters of stars that are somewhat smaller. The idea is you use radio telescopes and you link these radio telescopes together to be able to serve as an interferometer, so to speak. And you can also do this somewhat at optical wavelengths as well, but it's a lot easier to do it using radio telescopes because of the fact that it's a lot easier to convolute the individual signals from each of the individual radio telescopes. It's easier to do that over large distances than it is with optical telescopes. So, for example, the Very Large Array in New Mexico. Now, we can also indirectly determine stellar diameters when you have eclipsing binaries. Remember the transit method for planetary detection? Using the transit method and the timing of how long it it takes a star to get dim when a planet passes in front of it, that allows us to determine the diameter of the planet. Well, you can also use that same method to determine the diameter of a star. For example, how long a star stays dim when another star passes in front of the star. Again, this only works when you have a binary system with edge-on orbits. If it's not an edge-on orbit, then you're not going to be able to glean any information from this. But based on how quickly the dimming occurs and how long it stays dim, you can determine the diameter of each of the stars in an eclipsing binary system. So that idea is kind of summarized right here. And here it is again in pictorial form. The time that it takes to go from brightest to dimmest in this perfectly edge-on example will allow you to determine the diameter of the small star in this system. How long it stays dim allows you to determine the diameter of the large star in this system. Now, the largest stars in diameter, for example, VY Canis Majoris is a red hypergiant, which is just another kind of an extreme example of a red supergiant. These things can be bigger than Saturn's orbit. And Betelgeuse, again, it has an orbital diameter of about 8 or 9 astronomical units, so an orbital radius of between about 4 and 4.5 astronomical units, maybe as far as Jupiter's orbit, if you accept some of the larger estimates for Betelgeuse's size, which is kind of hard to determine. But one of the problems with these really, really big red supergiant stars, it's kind of not always very well defined exactly where the outer extent of the star ends and where the interstellar medium begins. So that's especially difficult with VY Canis Majoris, for example. So other things that we can determine with stars. For example, surface temperature. Well, that's found by fitting a blackbody spectrum to the intensity versus wavelength plot. Chemical composition, we get that from the spectral lines when we take stellar spectra. The luminosity of a star, well, you measure the apparent brightness of the star, in other words, its apparent magnitude, and then turn that into a luminosity. There's a formula for that. And then use the fact that brightness is equal to luminosity over 4 pi distance squared to determine the star's luminosity, assuming that you know the star's distance. How fast it's moving toward us or away from us? Well, that's the shift in the spectral lines in the star's spectrum. The rate of the star's rotation, though, can also be determined based on the width of the spectral lines. In other words, as a star rotates, well, some of that star is moving away from us, redshift, some of it's moving toward us, blue shift. So the width of those spectral lines will allow us to determine the star's rotation rate. The mass of a star, well, we've already talked about that. That was the big thing in the discussion so far today. And the diameter, either directly measure it using an optical telescope or use interferometry, especially with radio telescopes. Now, the smallest stars that are out there, and in some ways these aren't really real stars because they're not actually participating in nuclear fusion most of the time unless they're going nova, or in extreme extents, type 1a supernova. But white dwarfs are very special. These things are about the size of Earth, and they will have a mass on the order of our Sun's mass. In fact, our Sun will eventually leave behind a white dwarf core. When our Sun does that, the remnant will have a mass of about half of our Sun's current mass, and the object itself will be a little bit larger than Earth. So that makes these things extremely dense. So we're talking about 2 million times the density of water. So a teaspoonful of these, assuming that Earth's gravity was in place, would weigh about 5 tons. So that's how dense these objects are. And, as we've already mentioned, we know of a white dwarf. In fact, we know of lots of white dwarf stars. One example is Sirius B. This is probably the most famous example. It's the orbiting companion of the brightest star in the night sky, Sirius. And originally this thing probably started off with about 5 or so times the mass of our Sun. Right now its mass is 0.98 times the mass of our Sun. But its radius is smaller than Earth's radius. And for reasons that we're going to discuss in a future video, Sirius B is a situation where if you were to add more mass, then it would actually get smaller. In fact, any white dwarf star is like that. It's a special state of matter called electron degenerate matter. And when you add more mass to it, it gets smaller in size. So you might wonder, is there a limiting mass where you would get it so small that something spectacular might happen, that it might start to try to undergo collapse? It turns out there is. That's the Chandrasekhar limit, and we're going to discuss that in a future video. Now back to Sirius B. Its temperature, it's very small, again, about smaller than Earth size. Its mass is about the mass of our Sun, but its surface temperature is 25,200 kelvins. And actually, because of that surface temperature, and what we figure it had to have started out as based on its original mass and its current mass and all that, we realized that the Sirius system is 120 million years old. So in fact, more precisely, it's been cooling for 120 million years. It was undergoing the rest of its life for probably, well, that's something that you can calculate out, but in the next discussion, you are going to calculate out that result. But just a quick little mental calculation there, rough order of magnitude. The star itself, when it should have been on the main sequence, probably for a little bit less than 200 million years, if you were to apply the formula there, which, again, we're going to get to next time. Now, how bright is this thing? I mean, surface temperature 25,000 kelvins. I mean, one of the stars in Orion's belt has a surface temperature of that, and that thing's like hundreds of thousands of times as bright as our Sun, probably. Well, the luminosity of Sirius B is less than 1/400th the luminosity of our Sun. So we're talking about something that's very dim. Well, why is it so dim? Well, even though its temperature is very high, its size is very small. So remember, yes, luminosity does go as temperature to the 4th power, but it's also proportional to surface area. So this thing is much smaller in size than our Sun, so you have to take into account that much, much smaller surface area and tie it in with that larger increase due to the higher temperature, and you get that it's less than 1/400th of our Sun's brightness. Surface gravity there, almost 400,000 times Earth's gravity, so you would be crushed there. Now here is a picture of the Sirius system, and in this case some image processing techniques have been used to reduce the brightness so that you can actually tease out the companion star, but you can actually see the companion star right here. This is Sirius B, the white dwarf. Now this is taken in the visible part of the spectrum. Let me show you an X-ray image. This is an X-ray image of that same system, except here's the thing. The really bright thing here, that's the white dwarf. The dim thing here is Sirius A, the star that we consider the brightest star in the evening sky. Now, what about stars that were just not massive enough to have enough energy in their cores to start the proton-proton chain? These are what we call brown dwarf stars. Technically, they are not actually stars. Now, do not confuse brown dwarf stars with black dwarf stars. Black dwarfs are stars that do not exist yet. The universe has not been around long enough yet. But eventually, stars like Sirius B, they're going to eventually cool down as they radiate off into space. Remember, they don't have really an energy source to speak of anymore, so they're just very gradually cooling as they radiate off their energy into space. But in something on the order of about 1 quadrillion years, these will end up being cool enough that we will call them black dwarfs. In other words, they won't really be detectable. But there are other objects called brown dwarf stars. So here's the situation with brown dwarf stars. It turns out that if you start off with a mass of something forming into a star-like object, but it's less than about 1/12 the mass of our Sun, it's not going to have enough energy to start the proton-proton chain. The temperature and the pressure in the core will just not be high enough. However, if it's more than about 1/100th of our Sun's mass, in fact, to be more precise, putting it in terms of Jupiter's mass, if it starts off with between 13 and 78 times the mass of Jupiter, it turns out that the temperature in the core is high enough that you can actually have have nuclear reactions with whatever deuterium happens to be present there. Remember, deuterium actually formed during the Big Bang, so there is a decent amount of it in our universe. About 1 out of every 1,000 hydrogen atoms on Earth is a deuterium atom. But deuterium has a very strong, very large nuclear cross-section. It very easily participates in nuclear reactions. But it doesn't participate in chain reactions. You can generate energy from that, but you don't end up producing enough after that to really be able to keep the process going. So yeah, deuterium that's there, that's going to participate in nuclear reactions, but once the deuterium's gone, that's it. In fact, with stars that start off between about 13 and 78 times the mass of Jupiter, that process only takes about 100 million years. So once the deuterium's gone, it's gone, and then you just go back to being something almost kind of like a really massive planet. So the first such object to be discovered was the star Gliese 229b that was found in the year 1995, or actually its discovery was announced in 1995. There were hints of it before. In fact, let me just kind of skip ahead. This is a picture of Gliese 229b. This was the hint that was found back in an image published in 1994 from the Palomar Observatory, but we wanted something better than this kind of blurry thing here. Well, in comes the Hubble Space Telescope, and yep, there it is. No doubt about it. That is a brown dwarf star. Now, this is an artist's conception of what a brown dwarf could potentially look like if it's just kind of out on its own. These would be very stormy places, and you're dealing with situations where the outer atmosphere of it might actually at times be relatively cool. There are some very cool brown dwarf stars out there. In fact, the lowest mass of these things actually have temperatures that are on the order, sometimes in the outer atmosphere, of room temperature. But again, they are very stormy places, but it kind of makes people wonder, like, what could it potentially be like in the atmosphere of a brown dwarf? And there could be certain levels where temperatures would be consistent with what you would want in order to have life be sustainable. Now, you probably wouldn't really have a good energy source for this life, but nonetheless, it does make it kind of interesting to speculate. So back with this image of our, well, I shouldn't say image, but artist's conception of a brown dwarf. Why do we think that they might look like this? Well, it turns out that we have found one brown dwarf that rotates every 2.5 hours. That is quite fast. Remember, our sun takes on the order of about 30 days to rotate once. But every 2.5 hours, we notice very distinguishing changes in brightness, and these occur fairly regularly and only fade over a course of years. So we recognize that that is likely due to the presence of storms like this. So here is a diagram showing some of these brown dwarf type objects as they compare with our sun, which remember is a G2 star. Now, the red dwarf star, in fact, here I'll show you an image of a red dwarf star. We're going to talk about that soon. This right here is a red dwarf star, Gliese 229a. It's being orbited by its companion, the brown dwarf, Gliese 229b, but a red dwarf is actually a real honest-to-goodness star. But here you're actually starting to get into the brown dwarf territory. And we actually have found brown dwarf stars that do have atmospheric temperatures that are fairly similar to room temperature. Now, just kind of a summary, objects that are less than about 1/80th the mass of our sun, that is less than about 13 times the mass of Jupiter, these are generally called planets. So Jupiter is, for example, 1,047 times less massive than our sun. So sometimes people say, oh yeah, I've heard that if Jupiter was a little bit larger, it would be a brown dwarf. Well, it would actually need to be a lot larger in order to be a brown dwarf. It's much smaller than the cutoff for things that would be a brown dwarf. There are, however, kind of exceptions to this 13 Jupiter mass rule. For example, we have found extrasolar planets that don't really behave as brown dwarfs would be expected to behave, that are on the order of about 20 times the mass of Jupiter. So it's possible that we have some missing information here, but there is a little bit of wiggle room in this general rule. Now, what about motions of stars? So we've talked about line of sight velocities and everything with radial velocities, but stars can also move back and forth in the night sky, or at least they can move side to side. Some of these are exhibited with binary systems, but sometimes you'll have an overall motion. Now, I'm putting this discussion in the middle of red dwarfs and brown dwarfs because this is actually going to lead us to a very interesting star. So, a star's motion with respect to background stars is known as proper motion. That's the tangential component of its overall velocity. Radial component is measured with Doppler effect. Tangential motion is measured just by watching the star. The star with the largest proper motion is a star called Barnard's star. We've talked about Eugene Barnard before, but Barnard's star actually moves through the sky at 10.3 arc seconds per year. But other stars are undergoing proper motion as well. For example, here's the Big Dipper asterism right now. Here's how it was about 50,000 years ago, and here's what it'll be like about 50,000 years from now. Well, Barnard's star is actually doing this on timescales that we can recognize. For example, here's a picture of Barnard's star right here in 1950. Notice this little V of stars, and here's a picture of it again in 1997. Again, there's that little V of stars. So essentially, Barnard's star moved from about right here up to here in that intervening 47 years. Now, most of the time this motion is relatively small. It's really big with Barnard's star, a star you probably haven't even heard of, because Barnard's star is actually one of the closest stars to our sun. I think it's something like 6.6 light years away. But it's an example of a red dwarf star. A red dwarf star. Red dwarf stars are the least massive, coolest of what you can actually call stars. Real, honest-to-goodness stars, the ones that are in the process of undergoing the proton-proton chain or have done so in the past. There's another example of a red dwarf star, a 9th magnitude red dwarf called Gliese 710. It's currently 63 light years from us, but observations from the Gaia spacecraft indicate that in about 1.28 million years, it will only be 13,000 astronomical units away. Now, 1 light year is 63,000 astronomical units, and the closest star to our sun right now is Proxima Centauri, which is 4.25 light years away. But here we're talking about something that is going to be a little bit over 1/4 of a light year away from us. Sorry, actually a little bit less than 1/4 of a light year, a little bit over 1/5 of a light year away from us when it has its closest approach. That'll put it well inside of the Oort cloud of comets in the outer solar system. So when that happens, it's actually going to have an apparent magnitude of -2.7. That is a good Mars opposition. In other words, when every once in a while Mars has a very good close opposition, and it'll have an apparent magnitude of about like -2.7 or -2.8. Well, Gliese 710 will be that bright, and it'll be that bright for a long time. I mean, much longer than a human lifespan when that happens. Now, it's possible that this will cause some disruption in the Oort cloud and cause some comets to come to the inner solar system, but it won't necessarily give a hugely increased probability of a major impact event, in spite of my note that I have here. More recent studies are showing that this might not necessarily be the case. So what are these red dwarf stars, things like this Gliese 710 and Barnard's star? So I'll just say that red dwarf stars are stars that are actually just like our sun. They're just a bit less massive. They make up the mass range between about 0.08 and about 0.4 to 0.5 times the mass of our sun, depending on where you want to have your cutoff. And one of the big differences is that red dwarf stars will never end up actually undergoing one of the phases that our sun will have. Our sun will eventually end up going into the asymptotic giant branch when it fuses helium in a shell around the core, but a red dwarf star is never actually going to do that. It's just not going to happen in that case. Another big difference between our sun and a red dwarf star is that, remember how our sun has a radiation zone just outside of the core? Well, a red dwarf star is fully convective between the core and the outer layers, and that helps to recycle the material a lot better and give you a full distribution of that material, and therefore extend its life even longer than what you would normally expect. So that's the big difference between our sun and a red dwarf star. We'll have more to say about red dwarf stars in a future discussion, but I did just want to give something of an introduction to those now. These are the smallest things that you would actually call real stars. So we've discussed how red dwarf stars are the least massive of the main sequence stars, and I think we've also mentioned that blue supergiant stars are the most massive, typically, of the main sequence stars, even though they're not the largest physically, they're the most massive. So that turns out there is a relationship between the mass of a star when it's on the main sequence and its luminosity, how bright it is. Remember, the main sequence is when the star is in its core hydrogen-burning phase, which does not last forever. But in the case of something like Proxima Centauri, a red dwarf star, you're talking about something that is a very small percentage of our sun's luminosity. But something like R136A1, the most massive star known, a blue supergiant at 265 times the mass of our sun, that thing is 8.7 million times as bright as our sun. So how do we figure out such a relationship? Well, what you can do is you can plot the luminosity of a star against its mass, and with proper units and proper scaling of the axes, make it a log-log plot, which is what this is. You can then take the slope of your log-log plot, and that slope will tell you the power. And in this situation, it turns out that there is a relationship such that luminosity is proportional to a star's mass to the 3.5 power. Why? Well, that's just how it is. It has to do with the rate at which stars fuse hydrogen into helium. Now, this only works for main sequence stars. In other words, if the star has left the main sequence, if it's not fusing hydrogen and helium in the core anymore, the relationship doesn't work. Or if the star is too massive, if it's more than about 40 times the mass of our sun, the formula doesn't work either. In fact, there's another formula that starts to kind of level off toward like luminosity proportional to mass to the 1.75 power once you start getting close to about 40 times the mass of our sun. So let's look at an example. Calculate the luminosity of a star that is 7 times as massive as our sun. Well, we said that it's proportional to the luminosity is proportional to mass to the 3.5 power, but how can we actually calculate the luminosity itself? You need to know the luminosity of our sun. Well, I know the luminosity of our sun, and guess what? You do too. What's the luminosity of our sun? I'll give you 2 seconds to think about it and pause the video if necessary. So I'll tell you the luminosity of our sun. It is 1 solar luminosity. So you compare the star to our sun. We set up a ratio. We're doing the ratio method. We say luminosity is proportional to mass to the 3.5 power. So the ratio of the luminosity of those two stars is equal to the ratio of their masses to the 3.5 power. Well, the luminosity of our sun is 1 solar luminosity, so we'll just compare the star with our sun. So, doing the calculation, you just plug in the star's mass. Well, the star's mass is 7 solar masses, so the solar masses bit cancels, and you get that the luminosity of the star compared with the luminosity of our sun is about 907, so therefore the luminosity of such a star is 907 times the luminosity of our sun. Let's take a look at another example. In fact, please pause the video and try this example on your own before proceeding. So, same deal as before. We have our given written down, a 0.78 solar mass star. Its luminosity, therefore, when you plug in the numbers, cancel your units again, and rearrange, you get that the luminosity of the star is 0.419 solar luminosities. Again, the 0.419 comes from taking the number 0.78 and raising it to the 3.5 power, and realizing that, okay, solving for L here, you multiply both sides by L sun, you get that L is 0.419 L sun. Now, stars also form clusters, and clusters can be quite massive. First of all, there are open clusters. Open clusters tend to be relatively young. The Pleiades is perhaps the most famous example of an open cluster. The Hyades is also an open cluster. So is the Beehive cluster. All of these have been on our constellation quizzes. So here are the Hyades, and there's Aldebaran, which just happens to be lying along the same line of sight, but this is the Hyades cluster. And look here, there's another open cluster in here. I don't know right off the name of this one, but this is probably one of Charles Messier's objects. But the Beehive cluster is another example of an open cluster. Here's a picture of the Beehive cluster. Globular clusters are something completely different. These things tend to have tens of thousands to millions of stars. Open clusters tend to be young. They'll have maybe hundreds of stars. Globular clusters tend to be very old. In fact, they're often, in a lot of cases, some of the oldest objects still around in the universe. In fact, some of them in our galaxy are about 13 billion years old, making them the oldest objects in our galaxy. Our galaxy has a couple hundred of these things, but the galaxy M87 has over 10,000 globular clusters. The stars in globular clusters, well, these are going to be old stars, which means that they're not going to be all that massive. Typically, they're between about 8% and 90% of our sun's mass, the individual stars. Here's a picture of a globular cluster, picture taken from the Hubble Space Telescope. Here's a picture of a globular cluster orbiting the Andromeda Galaxy, and here's another picture of a globular cluster in our galaxy. The centers of these things sometimes have what we call intermediate mass black holes. We'll have more to say about those in a future discussion. But long story short, these are very dense stellar environments. I mean, the night sky in a globular cluster would just be absolutely awesome. I mean, you would have, let's say, like 100 stars, maybe more than 100 stars that are brighter than Sirius, and the brightest stars in the night sky, if you were on a planet orbiting around a star in a globular cluster, the brightest stars would be around like -8 in apparent magnitude, so easily visible during the daytime. In fact, the night sky would be so bright that it wouldn't really be all that dark at night. You would easily be able to see your way around. A very nice example of a globular cluster in our galaxy is the Hercules cluster. It is just barely visible with the unaided eye. It's in the constellation Hercules. This has something like on the order of about 1 million stars, and I just mention it because it is one that is visible to the unaided eye even from our latitudes. Yes, Omega Centauri is visible to the unaided eye, but it's so low in altitude that it's very difficult to see. And this is a picture of these central regions. Yes, the stars are packed very closely together. Again, you're talking about 1 million stars in a region that's maybe only about 100 light years wide. Now, there's another example in the Large Magellanic Cloud that we know to be 11.7 billion years old. How do we know that age? Can you guess? Well, it's based on the Hertzsprung-Russell diagram. We will have more to say about that in the next discussion, or one of the next discussions, but we can figure out the age from the Hertzsprung-Russell diagram. The older stars live longer, the younger stars move off of the main sequence earlier, and in a cluster, all the stars form at about the same time. Now, Omega Centauri is the most massive globular cluster we know of in the Milky Way, but we now recognize that technically it is not actually a globular cluster. It's actually the core of a dwarf galaxy that had its outer stars stripped away. But it is visible from the latitudes of northern and central Virginia, just barely. If you want to look at it at the best time of year, that would probably be around midnight, around mid-April, but it would be just a few degrees above the southern horizon. There are also things called superstar clusters. These are kind of the cores of things that may eventually end up forming into globular clusters. We've already seen some before. R136, this is a superstar cluster. Very pretty picture. Another one, Westerlund, I think, is another example of a superstar cluster, and there are also a couple of other of these things in some nearby galaxies. But these are probably the early cores that will eventually form globular clusters after the most massive stars explode. But right now, superstar clusters have very massive stars, very bright stars, a lot of stars that will eventually explode into supernovae. So that marks the end of the surveying the stars part of this unit. So we've covered a lot of material in here, and this is kind of building the way to discuss the lives and deaths of stars, which will be the subject of the next PowerPoint set of discussions. So hope to see you then, and if you have any questions, please let me know. Thank you.